So how do you deal with repeated real poles? So in the individual real poles, your denominator looked something like, usually there was an S there. There didn't have to be, but usually there's an S there. If we have a step change input, for example. And then you have an S plus A1 and an S plus A2, and you could have any number of those S plus A's, right, depending on what your system is. And that was individual real poles. However, sometimes your poles are repeated. And so, for example, you could have your denominator be S plus A quantity to the nth power. When that happens, you can't do the method that we taught you for individual real poles. That'll get you a certain number of coefficients, but it won't get you every single one. Okay, so we're going to work out how do you do that. How do you actually deal with this particular situation? Okay, so since our denominator is defined that way, let's write out the whole thing. So let's say we are in this situation where y of s is equal to our numerator, n of s, over s times the quantity s plus a to the nth power. And we partial fraction expand that. You get c0 over s plus c1 over s plus a plus c2 over s plus a quantity squared plus cn over s plus a to the nth power. Now, if we operate as we did before by clearing the denominator, if I multiply both sides of the equation by what's in the denominator on the left-hand side, I get n of s is equal to c0 times s plus a quantity to the nth power plus c1s times s plus a to the n minus 1 plus c2 s times the quantity s plus a to the n minus 2 plus cn times s. Now in this case, we only have two poles for our denominator. We have s equals 0, and if we substitute that in, all these terms here, c1 through cn, they cancel out, and so it can get c0 that way. But we only have one other pole, and that's s equals minus a, and if we plug that in, every single term cancels out except for the final one. And that's it. So we can't get any of the other coefficients by just substituting in some value of s. So there's a way to handle this. And the way to do it is to expand out all these binomials and group everything into like powers of s. So I don't want to expand out s plus a to the nth power. Let's just say that n equals 2, right? So that's just the easiest way to talk about it, right? So that it's the simplest example, a equals 2. And I'm going to say my numerator is some constant k, right? So in this particular case, y of s is equal to k over s times quantity s plus a squared, which is equal to c0, that was weird, c0 over s plus c1 over c1 over s plus a plus c2 over s plus a quantity squared. If I clear this denominator, then I get k is equal to c0 times s plus a quantity squared plus c1 times s plus a plus c2 times s. Now if we expand out the s plus a quantity squared, this becomes C0 times s squared plus C0 times 2as plus C0 times a squared. If I expand out this second term, so distribute s over the s plus a, I get plus C1 s squared plus C1 times s times a. Let's write it the other way, a times s, sorry, a times s plus C2s. So now what I've done is I don't have any more like parentheses in my problem, right? I've distributed everything. And now what I can do is I can group everything according to like powers of s. So for example, I have a C0, what's going on here? I have a C0 times s squared there. And I have a C1 times s squared there. The s to the first power terms, I have a C0 times 2 times a, and a C1 times a, and a C2. And then I have one constant term, C0 times a squared. So I have three different like sets of terms here. And furthermore, on the left-hand side, I have k, which itself is a constant term, right? So that gets grouped with a constant term. Rewriting everything, I have on the left-hand side a 0 times s squared plus a 0 times s plus a k as a constant term. And that's equal to, grouping like powers of s on the right-hand side, a C0 plus C1 s squared plus a 2 times a times C0 plus C1 times a plus C2, all of that quantity times s, so that's my s to the first power coefficient. And then finally my constant is plus C0a squared. So you see that both sides of the equation have been grouped according to what power of s they have, each term. And so now I can set the coefficients of each power of s equal to each other. So the equation for s squared becomes 0 on the left-hand side is equal to C0 plus C1. That has to be true. The equation for s to the first power is 0 equals 2a C0 plus C1a plus C2. And the equation for the constant term is k equals to C0a squared. So the substitution method is like easy. That's what you do with individual real poles, but you just can't do that here. And so you have to do something a little bit more complicated by like grouping everything together, multiplying out all the binomials, and multiplying binomials first, then grouping everything together. And you end up with these three independent equations. From there, you can solve for your three independent coefficients. Solve for C0, C1, and C2 using those three equations.